Hi, this presentation is about biocompilation, a method which assembles languages to express biological connectivity. My name is Adriana Climescu-Haulica. I come from Cambridge, United Kingdom. Avantiv is a company focusing on high-level mathematical modeling. The progress made by the computational biology is huge, so the future is great. But the expectations are to have a better understanding of the cell and consequently of the human biology. The benefits will be great for the molecular system medicine, and the physiological mechanism has to be explained up to the omics level. The impact of the system biology will be, in this case, scale. Plenty of resources are available to fulfill our task. We have data, we have tools, we have a new healthcare mindset, having the feedback from the use of the biomarkers as molecular signature in the hospitals. We have large biological networks developed and have networks of networks. So it is very important for us because we can use that further, and they are spanning main direction of the biology. What I like to stress here is the fact that we have complex mathematical concepts which are very sparsely used in biology, and this is a big potential. The main fact is the following observation. The concept of networks, it was imported in biology from engineering. It was translated actually. Copy and paste. It's not appropriate for the biology. Not because it has not his interest. Sure, it has his interest and we showing use that. But it's too limited, it's too schematic. In engineering, the networks works very well. In biology, it's prone to mistakes actually. Because it's too simplistic with all this information. It's miss flexibility. It doesn't show, it shows dynamical modeling of the biology only in the single way. Actually, how only, we say, unidirectional dynamics, which in biology you have unidirectional dynamics. So, what we propose to overcome that? We propose to understand the communication, the biological connectivity as a communication between biological entities. Everything, other things, other language adapted to the situation we are in, and we construct that rigorously, mathematically with the compiler. The construction of the compiler follows from the following comprehension. Most important is to select the biological system we like to modelize, the biological connectivity at each level. Adapted to that, we have to construct some bioalgebras. This is the key element, main ingredient of our construction. These are the bricks actually of the compilators. Once the bioalgebras are well defined, the steps are easy to follow. We have the regular grammars associated with these bioalgebras. We have the language generated by these regular grammars. And we define four operations: union, intersection, Markov concatenation, and logical juxtaposition. And after that, we have the compiler seen via the large sense formal language characterizing it, which is the closure with respect to these operations. After that, we have the theorem saying that we can build a unique minimal automaton accepting this compiler. And more than that, this construction is very rigorous because it produces a decidable state complexity. Let's see a nice example. As I said, it's very important to choose not important in biology, something which is very hard to describe. Here we notice that we have the lymphatic system and immune system, which are so strongly bind, such that it's very difficult to express biological connectivity between them. So we, after result their separation via the endocrine system, Working with our compiler to the dynamic normalization, actually, technically what we do, we arrive at the same denominator via the construction of our bioalgebras. The output of this exercise is that we may hope to build an exact medicine in the future where the rigidity and traceability are at high standards. But the compilator can be used also in the bigger setups, application, for example, for diagnosis and therapy. Let's see here. So we integrate our compilator in the process of decision where what it is as input are hypotheses, what is given output are proofs actually. Work with compilator. So the language will be quite different here. So you have bigger entities. And it's really powerful because it comes with robustness and trustability. This is the very complex architecture and having the references this work of us. Here are some of our references with our thanks to you for watching this presentation.